So now we are going to take up examples of solving first order differential equations by using substitutions. Now, of course, there are many types of first order differential equations, and there could be many substitutions, but we are just going to, just to get a feel of it, take two simple ones, okay? So let's take this one as our first example. So in here, what we notice is this, that look at the degree here, that is 3. And here also the degree is 3. So what we may try is this. So let us try a substitution like y is a function multiple of x. That means this u is a function of x. Okay, so that's what we are going to try, and you may see that since we are taking y as ux, because here we have degree 3, here we have degree 3. Okay, so x cubed could be factored out and they will cancel. All right, so we have uh, y equals ux, so dy dx will become how much? Let's use the product rule. So u dx, I just wrote it even though I didn't have to for a class like yours. So we got this, and you know this quantity is 1. So what we got is that we got dy dx equals simply u plus x du dx. So if we substitute in the original equation, what we get is that we get here we have ux square, okay, and here we will get what? Ux cubed, which implies that we got and again we should have written, yeah, let's write it anyways, we should have written it in terms of du dx rather than dy dx. So what we will get is now that we are going to get ux cube here, and here x cube can be factored. All right, and you got u cube minus 1. Okay, so I hope I'm not doing algebra too fast or too slow depending on who is listening. Now first let me fix a simple mistake here. Here I should have gotten u square, and here I left this as simply u, so I should change this to u square. Okay, and here I am writing x not equal to 0 because our initial condition is y1 equals 2, so we can safely assume that x is not 0, because as you might see, we are going to be canceling x cube on the two sides, and what that will give to us is that here x cube is out, or we divided by x cube. So this is what we got here. So we have now, let's multiply this out. We got u cubed, okay, plus x u square du dx, okay, and this is the textbook example, so it has just been, you know, very well, like very conveniently formulated for us. So now what's going to happen? This u cube and u cube on this side, they will cancel, and so what we get next is, so cancel the u cube on both the sides. Okay, so we get this equals -1. So what we have is that So we have a separable differential equation, right? So this can be, so if we use the separation of variables, what we get is u is square du, sorry, du equals negative dx over x, right? Okay, and that will give us u cube over 3 when we integrate the two sides, right? So u cube over 3 equals negative natural log of absolute value of x plus a c. And if you want, you can write u back in terms of x and y, right? That is, remember this, y is u times x. So u is going to be y over x, all right? So if we substitute that in here, what we will get is that we will get y cube, okay, divided by 3x cubed, okay, equals negative natural log of absolute value of x plus a constant. Now we can bring this in, that is y for x equals 1 is 2. So that means if we substitute x equals 1 in here, okay, what y will become is y will become 2. So what does this give us is, or what this gives us is, natural log of 1 is 0. This is 8. And this is 3 downstairs. So c is simply 8 over 3. All right. Okay. And so here is our final solution, okay, of this differential equation, and we are leaving it in the implicit form, all right, because we were not asked to do it explicitly, so we can just leave it like this, all right. So let's go to next example, and that also I'm just pulling from the textbook. So let's take this as our second example. So in here, I mean, it's not really given as clearly as the previous one was. So let's just go ahead and play with it a little bit, okay? So we can do this here. First of all, we may simplify it by dividing by x, because looking at our initial condition, we can safely assume that x is greater than 0, and it will have to be greater than 0 for the equation to make sense. So we may do this here. First, we may just divide y by x, okay? Sorry, the entire equation by x I meant. So what will happen then is that this x is out. Now let's keep doing algebra, and further algebra tells us what? That natural log of x minus natural log of y. Okay, and we can keep y also away from 0 according to our initial condition. So what we get then is this would be ln of x over y, right? Now here we got y over x, here we got x over y, but we know the property of natural log. If we just take the reciprocal, what will happen is sign will be -1, and we simply get a -1 in front, okay? So what I meant is that we shall have, we can write it as negative natural log of y over x. Now, if you look at this format, looks like that, we may try y equals ux again. I said try because I'm not saying that that is definitely going to work, but we are just going to try and see if it works. All right. So here again, as before, or as in the previous case, I'm not writing the details. Okay, so this is u plus x du dx, and let's see if the book gave us a question designed in a way that it could be done easily like this. So since y is ux, y over x is u, so we got a u here again. And for this one, what we shall have is u plus x du dx. Okay, so this is what we have for the whole thing, and now let's see what we get from out of it. All right, so at the moment, the very first thing that we will have to do, I don't see a way around it, is to multiply these out, or what you call the FOIL method. If you did algebra in a class that did do FOIL's method or FOIL method, so if we multiply, what do we get? Negative u ln u, and then we get negative, uh, let me just put ln of u here in parentheses, this when I'm multiplying with this. So ln of u x du dx, okay, and then we are multiplying with 1. Well, we had one nice thing. These u's will cancel. Minus x du dx, right? So we got all that. So let's just go ahead and carry our cancellation out. That is, this u is cancelled by this negative u, and if we look at the whole thing now, then what we have is, okay, yeah, looks like it might simplify. Okay, so here we go. So what we are going to do here is, let's just factor x du dx out. So what we get is, we simply get that, right, by factoring that out. And now we can separate the variables, as you can see this dx over x, or x over dx. We can bring that up here. I'm just dropping the negative signs. And then this ln of u ln of u, I'm taking it down here as u ln u du. Okay, and that is a 0. So this one is quite easy, that we will have simply natural log of x. And for this one, let's just, go ahead and review our substitution rule. All right. So we got here ln of u minus 1 over u ln u du. So if we took ln of u as, say, w, then what will happen? 1 over u du would be dw, right? So this quantity here is u du, so that becomes dw, and this is w minus 1 over w, that is 1 minus 1 over w. And here we saw we have both x and y as positive quantities, so w would be positive. Okay, so this integral would be simply w minus ln of absolute value of w, right? So if we write it in our type setting, what we get is this. Now we should just first note that what we have here is ln of u, because that's what we are writing for w, and that equals here ln of u. All right, so So when we go ahead and write the solution, here the antiderivative is ln of x, and what we found for this was that this was simply ln of u, okay, and then minus ln of absolute value of ln of u, and that equals what? A constant, okay? Now I just discovered an algebra mistake that I made. That is in here when I took negative x du dx as a common factor. This should have been plus 1, so this would be plus, and this would also turn into a plus, okay? So what we have is, let's write it out in the original, in terms of the original variables. So you have ln of who? Y over x, all right, plus ln of, then ln of y over x again, and that equals, let me just bring it down here because I'm going outside the recording area. And right here, you can see we can cancel ln of x. So that's going to make the load lighter, okay, because this becomes ln of y minus ln of x plus all this equals c, right? Okay, so now let's cancel ln of x with ln of x and obtain, we are simply doing algebra now, but that's okay. We are doing math, and so, and algebra is nice, I like it. So anyway, so we got this whole thing is this, and notice this, we can write this little c as ln of, say, another quantity, say big C, all right? So what will happen now is that here I have sum of two natural logs, so that will be the natural log of appropriate product, and so there we go, we got ln, and then y times, sorry, y times absolute value of ln of what? Y over x, right? And that equals, so that equals ln of big C, sorry, ln of big C, and then ln, or natural log, is a 1 function, so we get this quantity equals C, and our initial condition is that when x is 1, y is e. So what we get by using that, rather this implies that, okay, that is when x is 1, y is e, so we get ln of e will be 1, so c simply turns out to be what? That turns out to be e. So our final solution is, we had a lot more algebra in here than calculus, but it's all right. Okay, so this is our final solution of this initial value problem. Now let's take another example from the textbook, and here the book tells you that this is a Bernoulli equation, and you can just put that in that set format, but let's see how we can think about it directly. Okay, so in here, if you look at it, we can't see any way of separating the variables, but we got dy dx here. It's a linear differential equation. We may just consider trying dividing everything by y squared, and of course we have to assume then that we are not keeping y equals 0 in our domain or in our discussion. And now you can see that we can transform it into a familiar form. Remember this, that if you have an equation like dy dt equals a function of, t times y equals, or yes, I can write dy dx, okay, equals qx, then I could solve it by using the method of linear equations. So in here, you may think of substituting -1 over y for another variable, say v. And then what will happen? -1 over y, the derivative is 1 over y squared, and that should come easily under control. That is, say if we put this as, say, u, then what will happen? The derivative with respect to y, the derivative with respect to x is going to be simply this. So 1 over y squared dy dx, that turns into du dx, and this equation will change to simply du dx, and then minus how much? Minus u equals e to the x, right? Now, it is a linear equation in u and x now, right? Now, one moment, remember this, that we had -1 over y as u, so this should be positive u, right? So what your integrating factor would be then? It would be the integral of simply 1, which will become how much? Simply e to the x. So what our solution will be if we apply our linear equations method, u times e to the x equals integral, right hand side is e to the x, then e to the x is our integrating factor as well. So we get e to the 2x dx, right? So what we have is, we got e to the, 2x dx, and e to the 2x, if you make substitution, the entire derivative would be how much? That would simply be 1/2 e to the 2x, okay? And then plus a constant, right? Or in other words, you may write that this is, for you may write -1 over y back, all right? And you may solve for y if you would like, or we may just leave it like this, okay? Depending upon the situation we are in, okay? So let's just quickly redo an example like this. So now in here, this is a question from the textbook again, and it doesn't fit any pattern that the textbook shows you. So our judgment call may suggest that we may simply try substituting for this. And here we are just solving every question conveniently, but many cases this will not even give us solution. So what I'm doing is I'm differentiating it just to relate dy dx with du dx, and here we go. We got the relationship as this, and that gives us that dy dx is going to be du dx minus 1, okay, where u is this quantity, x plus y plus 1. So what we get here is this, that this implies that du dx minus 1 equals how much? U square, right? And that implies that du dx would be 1 plus u square, right? Now we have, now we can separate these equations and do the antiderivative as, or the integral as du over 1 plus u square equals simply the antiderivative of 1, which gives us what? Which will give us tangent inverse of u equals x plus c. And I mean, we can just go ahead and simplify it. It won't take more than a minute. Okay, so we got what? X plus y, sorry, plus 1 equals x plus c. And well, since it's easy to solve it explicitly here, let's do so. Just to be polite. It was not too complicated in the earlier one also, but here it's really, really easy, right? So here we can solve for y, negative x minus 1 plus tangent of x plus c. So that's your final solution. So let me know if you have any difficulty with any other examples in the book or on the assignments, okay?